So today we're going to be looking at some more related rates type problems. We kind of looked at the basic problems the other day, and now we'll be kind of looking at a little bit more advanced type problems. Some of them will be involving trig. Example one is similar to what we went over last class with the right triangles. You'll see that we'll be able to draw a picture and model this using our Pythagorean theorem, the x squared plus y squared is equal to z squared. So I'm going to draw a picture as I read through this. It says a given moment, a car is 30 miles north of an intersection. Intersection here, and I'll draw my car 30 miles north of that. And we know the car is traveling towards the intersection at 45 miles per hour. So I'm just going to make myself a little arrow indicating my car is coming this way. And we know that it's traveling at 45 miles per hour. At the same time, a truck is 40 miles east of the intersection. So here's my intersection. I'm going to draw the truck somewhere over here. Traveling away from the intersection at 35 miles per hour. So I'm going to draw myself a little arrow indicating that my truck is driving away from that, and we know that it's traveling at 35 miles per hour. I'm also going to put its distance, which is 40 miles. And we want to know, is the distance between the vehicles increasing or decreasing at that moment? And then I want to know at what rate. So we want to know basically this rate of change. So the diagonal here, rate of change. So I can make this into a right triangle. I'm going to label my bottom side as my X. I'll label my vertical side as my Y. And these 35 and 45 are actually our rates. So that's the rate of change of X and Y. So I'm going to label these as dx dt, and dy dt. So then, using the Pythagorean theorem, I should be able to figure out what this kind of diagonal distance is. So 40 squared plus 30 squared, and then take the square root of that. I believe that should give us a 50. And we want to know, well, what is this rate of change? What is dz dt? So setting up our x squared plus y squared is equal to z squared. Again, since this is modeled by a right triangle, we can set up this Pythagorean theorem and then take the derivative, 2x dx dt plus 2y dy dt. It's going to be equal to 2z dz dt. And we can fill in what we know. So it's going to be 2 times 40 times 35 plus 2 times 30 times, and we have to be careful with this rate here. So since this length, or since this car is heading towards the intersection, this length here is actually going to be getting shorter as the car travels. So this rate, this dy dt, is actually going to be a negative 45 because this distance is decreasing as the car moves. We can keep this rate, the 35 miles per hour, positive because as the truck moves this way, this distance is increasing or getting longer. So when I plug in my dy dt, I'm going to make that a negative 45. And then on my other side, 2 times 50, and I don't know what my dz dt is. So doing a little bit of algebra over here, I believe this gives me a 2800 minus 2700, and that's going to be equal to 100 dz dt. So I end up with 100 is equal to 100 dz dt. So that's going to tell me that my dz dt, or my rate of change between these two vehicles at that moment, is actually going to be 1. And it's asking us two things. Is the distance between the vehicles increasing or decreasing? Well, since this rate of change is positive, we know that the distance between the vehicles is going to be increasing. So the distance is increasing, and I know that it's going to be at a rate of 1 mile per hour. All right, so let's look at a problem that's a little bit different. We didn't see these types of problems in our notes the other day. So an observer stands 500 feet away from a launch pad to observe a rocket launch. I'm gonna put my little person here. Here's my rocket. That's a terrible drawing, but you know, get the idea. And I know that this distance is 500 feet. The rocket blasts off and maintains a velocity of 800 feet per second. So the rocket is going to go straight up into the air. So I know that its movement is going upwards, and I know its velocity is 800 feet per second. And we can assume this scenario is going to be modeled by a right triangle. So I'm going to make this into a right triangle, put my right angle down here. We want to know how fast the angle of elevation from the observer to the rocket is changing when the rocket is 1,200 feet above the ground. All right, so I'm going to make myself a little angle in there. I'm going to call it theta. And what I want to know is, what is d theta dt? How is this angle changing inside of this triangle as the rocket goes up in the air? So from what I know right now, I know that I have some sort of trig ratio here. And I know I'm going to have to use a trig because I'm working with a theta in here. So if I look at the two sides that I have labeled so far, I've got an opposite and I've got an adjacent. So I know that I'm going to be probably wanting to use tangent. So I'm just going to call this for right now, a tangent is equal to y over x. And the nice thing is I know that this distance here at 500 is not changing. This person is standing here watching this rocket launch up in the air. So what I know right now is that x is 500, and I also know that dx dt is 0. Because as the person is watching here, they're not getting closer to the rocket at all. So when I set up my trig ratio, I always like to kind of look to see where the side is that is not changing. And that's going to be the piece of information that's going to go in my trig ratio. So I know that x is 500, and I know that's not going to be changing at all throughout this problem. So I'm going to rewrite this as tangent of theta is equal to y over 500. And again, I'm putting that 500 in because I know that this distance is not going to be changing. That's a constant throughout the problem. So then I can go ahead and take the derivative of this, because I know I'm going to need a derivative because I know I have a rate of change here and I know I have a rate of change here. So if I take the derivative, I'm just going to actually clear this fraction by multiplying each side by 500. Or I take the derivative just so I don't have to use any sort of quotient rule. So 500 tan theta is equal to y, then I can go ahead and take this derivative. So 500 times secant squared theta, so that's the derivative of tangent. But remember that we also need to take into account the derivative of this variable, which is theta. So we're going to call this times d theta dt. And then over here, my derivative of y with respect to t is dy dt. Okay, so what do I know? Well, I know that I'm looking for d theta dt because that's what I'm trying to find here. How fast is the angle of elevation changing? I know I have dy dt, and I know this is, I'm just going to call this y since that's our vertical distance, and that's the rate at which y is changing. So I know I have dy dt, but I've got a problem here because I need to know what secant squared is, because if I'm looking for d theta dt, I need to have something to plug in here. So what we can use is we can think about the pieces of information that we haven't used yet. We haven't used the fact that we know that the rocket is at this instant 1,200 feet above the ground. Well, that's giving us a y value. We know that this vertical distance is going to be 1,200. And knowing x and y, we actually can figure out what this hypotenuse is of a right triangle, which we'll see is important in this piece here. So using the Pythagorean theorem, 500 squared plus 1,200 squared, take the square root of that, you get this distance to be 1,300. Okay, so think about this 500 as being multiplied by secant of theta squared times d theta dt. And I'm just going to go ahead and plug in my dy dt while I'm over here. So I'm going to plug in the 800. I'm actually going to set up something that's going to help me to actually find a value of secant of theta. So what I can do is I can go to my triangle and say, okay, well, I know the cosine of this triangle or the cosine of this angle. The cosine of this angle is going to be my adjacent over my hypotenuse, which I can simplify to be 5 over 13. And if I know the cosine, I can find the secant. So I know that my secant of theta is 13 over 5. And guess what? I can go ahead and actually plug that value in here for secant of theta. So I'm going to go ahead and say that's 500 times the quantity of 13 over 5 squared times d theta dt, and that's equal to 800. Now I've filled in all the other variables that I need to kind of find values for, and I'm left with the one thing that I'm looking to find here. So now it's just a matter of doing some algebra here. So I'm just going to go ahead and multiply that out. So 500 times 169 over 25 times d theta dt equal to 800. I believe when you multiply that out, that gives you 3380. And then when you simplify, d theta dt is going to be equal to 800 over 3380, which I can simplify to be 40 over 169. And I'm going to label this as radians per second. So that means that at the moment that my rocket is 1,200 feet above the ground, this angle is changing at a rate of 40 over 169 radians per second. All right, let's look at kind of a similar example. This one's going to be a little bit different because we're looking for something a little bit different, but it does involve some trig stuff. So we know that two people are 50 feet apart. One of them starts walking north at a rate so that the angle shown in the diagram below is changing at a constant rate of 0.01 radians per minute. So I'm going to go ahead and say, okay, right off the bat, I know that d theta dt is 0.01. And I want to know at what rate the distance between the two people is changing when the theta is 0.5 radians. So basically, I want to know what this rate is. That's my end goal, is to figure out what that rate of change is. So dx dt is what I'm looking to figure out here. Okay, so again, we're dealing with definitely a trig ratio because we're dealing with an angle. So what I have labeled right now is my adjacent side over my hypotenuse. So I'm going to go ahead and set up my cosine. And in this case, I already know what that kind of bottom distance is, so I'm going to fill that in right off the bat. So cosine of theta is equal to 50 over x. And then I know that I'm going to want to take the derivative of this. So you can do one of two things. You can clear the fraction like we did in the last problem, but if you do that, you're going to end up having to use the product rule over here because it's going to be x times cosine of theta. So what might be easier is to actually rewrite this term as 50 times x to the negative first power, because over here we can just take the derivative of cosine. Over here we can just use our power rule to take this derivative. So derivative of cosine is going to be negative sine of theta, but again we have to make sure that we are differentiating this theta, so d theta dt. And then over here, bring down the exponent, so that's going to give me negative 50x, decrease the exponent by 1, and then again we do have to differentiate that variable of x with respect to time, so dx dt. All right, so if we kind of think about what we have, we know we have a theta, so we could fill in the 0.5. We know we have a d theta dt, we can fill in over here. The problem lies over here. We know we're looking for dx dt, but we also don't have this x value to be able to use over here. So we're going to need to figure this out using some trig. So at the instant that we know this theta, again, we can kind of go back to our setup over here that we set up with the cosine. We can say that cosine of the theta of 0.5 is equal to 50 over x. So if we solve for x here, this is going to give us x is equal to 50 divided by cosine of 0.5. And I'm actually just going to leave this in exact form until like the very end when I actually figure out what my dx dt is, just so I can get kind of a more exact answer. So I'm going to fill in what I have here. So I have everything over here. I now know what my x value is, and I'm looking for dx dt. So negative sine of 0.5 times 0.01 is going to be equal to negative 50 times what we just found for x. So 50 over cosine of 0.5 to the negative 2 power times dx dt. And I'm just going to manipulate a little bit over on the right-hand side before I do anything with the left-hand side. So I'm just going to leave that as negative sine of 0.5 times 0.01. And over here, remember that when you have a negative exponent, what that really means is you have 50 to the negative 2 and cosine of 0.5 to the negative 2. Well, remember, to get negative exponents to be positive, you can flip their place in the fraction. So what we can actually rewrite this is cosine of 0.5 squared over 50 squared times dx dt. And the reason that this ends up being kind of nice is because then we can see that one of the 50s is actually going to cancel out in our numerator and the denominator. So we're left with negative sine of 0.5 times 0.01. And that's going to be equal to negative cosine of 0.5 squared over 50 times dx dt. And then what we would just end up doing here, you could just multiply by the reciprocal of this term over here to get the dx dt by itself. Running out of room here, but dx dt would be equal to, I'm going to put negative 50 sine of 0.5 times 0.01, and then that would be divided by negative cosine of 0.5 squared. So when you divide this out, again, remember that anytime we're working with radians, or sorry, anytime we're working with thetas, you should be using your calculator in radian mode. When you divide this, just be careful about how you are setting up your parentheses in your calculator. I believe that gives you about 0.311. And this rate of change, again, is only a length that is changing. So its units are just going to be feet per minute. So this is telling us that at the instant where theta is 0.5 radians, the distance between these two people are changing at a rate of 0.311 feet per minute. All right, so now that we've covered some trig stuff, we're going to be looking at some kind of geometry type problems, kind of revisiting a little bit what we talked about last time. I know that we talked a lot about the Pythagorean theorem, and we talked a little bit about volume and some areas, but now we're going to be talking about some cones and some cylinders. So example 4 is telling us that a water tank has a shape of an inverted circular cone with a base radius of 2 meters and a height of 4 meters. So I'm going to start sketching a graph or a picture here. So an inverted circular cone just means that my cone would be facing downwards. And I know that my cone has a base with a radius of 2 meters. And my cone has a height of 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, this is indicating that we're working with some sort of volume here because it's a cube. Find the rate at which the water level is rising when the water is 3 meters deep. Okay. So what I know right at the moment is I know that I'm looking for some sort of volume. So I'm going to write myself the volume formula of a cone, which is 1/3 pi r squared h. And I know that eventually I'm going to want to take the derivative of this. So the thing with this is, if you notice, you've got a bunch of things being multiplied together. So we would need to use the product rule. But there is actually a way that we can go in and rewrite this formula just in terms of one single variable. And that's going to be majorly helpful because then we don't have to use the product rule. And it's going to make our lives a lot easier when we go to actually kind of fill in what we know. So we know right now that dv dt is 2, and we know that we have a radius of 2, and we know that we have a height of 4. What we want to know is we want to know the rate at which the water level is rising when the water is 3 meters deep. So we want to know the rate at which the water level is rising. So if we think about like water being in this cone, the water level is going upwards. So what we want to know is we want to know the rate of change of the height because we want to know how that water level is rising. So we want to know dH dt. And we want to know dH dt when the height is exactly 3 meters deep. So if we're looking for dH dt, what my goal over here is to rewrite this formula just in terms of h, because that's the variable that I ultimately want to know what the rate of change is. So what I can do is I can go over back here to my drawing, and I'm going to actually extend the height kind of down to the point of the cone. And what this is telling us is we actually have similar triangles. If you notice, there's kind of this outer bigger triangle, and we have an inner smaller triangle. So what I'm going to do is I'm going to call this kind of smaller piece in here this little r, and I'm going to call kind of this smaller height in here little h. And I know that these are changing, or the rate of the height is changing. So I don't necessarily want to plug in that h yet because I know that this is going to be changing as this kind of situation is happening. So what I'm going to do is I'm actually going to write a ratio of my radius to my radius and my height to my height. So my radius of my cone is 2, and I'm going to say that that's going to be over my little radius of r. And then my height of my big cone is 4, and I'm going to put that over my height over here, or my little h. And this ratio is going to actually allow me to substitute something in for this formula. But what I want to substitute in for is I want to plug in for r. I want to get rid of this r so that I have all of this formula in terms of h. So what I want to do is I want to use this ratio to help me solve for r, so I can go ahead and plug that in there. So if I cross multiply, 4r is equal to 2h. This is going to tell me that r is going to be 2h over 4, which really means that my radius is going to be 1/2 the height. So now that I know that, I'm going to use this fact to substitute that quantity in for my r value so that I have this whole volume in terms of just the h. So when I plug in, I just have to be careful. I want to make sure to leave that 1/2 h in parentheses and then square it and then multiply by the h on the outside. Just going to do some manipulation here. So this is going to be 1/3 pi times 1/4 h squared times h. Combining my like terms, I believe that gives me 1/12 pi h cubed. And then I want to take the derivative of this because now it's just in terms of the volume and the h. And I know that I want to know what my dH dt is. And I know that I have dV dt. So my dV dt is going to be equal to, I'm going to drop down this exponent. Remember, this 1/12 pi is just a number. It's just a coefficient. So this is going to be 3/12 pi times h squared. And then I need to multiply by the derivative of h with respect to time. So dH dt. And then I'll just clean this up a little bit. So dV dt would be equal to, I'm just going to write this as pi over 4 h squared times dH dt. Okay, so now this other piece of information can come in. I know what dV dt is, and I haven't used the fact that I know what the height is. So at the instant that the volume is 2 meters cubed per minute, it's telling me that I want to know what the water level is rising when the h is 3. So at this point, I'm going to go ahead and substitute in my 2. It's going to be equal to pi over 4. I'm going to substitute in my h of 3. And then I'm going to go ahead and leave the dH dt as my unknown. And I'm just going to simplify over here. So 2 is going to be equal to, I'm going to write this as 9 pi over 4 times dH dt. And then I can just multiply by this reciprocal to get the dH dt. So dH dt would be equal to, I believe that's 8 over 9 pi. And since we're looking for the rate of change of just a height, remember that the height is just a length that's changing, so its units are just going to be meters per minute. So that means that at the instant where the height is 3 meters deep, the rate of the change of the height is changing at 8/9 pi meters per minute. And generally with these types of problems, we keep our answer in exact form, so you wouldn't want to get decimals for these. All right, we'll look at one more geometry type question. So this time we're talking about a cylindrical tank. So I'm going to go ahead and draw myself a diagram here. Okay, so my cylindrical tank has a radius of 5 meters. And it's being filled with water at a rate of 3 meters cubed per minute. So again, meters cubed per minute, that's indicating that this is going to be some sort of volume. We want to know how fast the height of the water is increasing. Okay, so we know that we're dealing with volume, and we know that we are looking for the rate of change of height. So we're looking for dH dt in this problem as well. So I'm going to go ahead and write out my volume formula, which is going to be pi r squared h. So for this one, we've got a couple of approaches that we can take, which is kind of similar to what we kind of talked about up here. We've got a volume formula in terms of two different variables. We could go ahead and use the product rule here. So let's actually look at that. So let's say one method, use product rule. So in order to differentiate this, my dV dt would be equal to, I would call my f the pi r squared, which would mean that my f prime would be 2 pi r dr dt. And then the g I would just call h, and g prime would be dh dt. So our dV dt would be 2 pi r dr dt times h. So I'm just going to write this as 2 pi r h dr dt plus pi r squared dh dt. Okay, so we know a couple things. We know that dV dt is 3, and it's being filled, so we know that our dV dt is going to be a positive. We know that the radius is 5, and we know that we want to find dH dt. So basically, that's all we know right now. So if we look at the variables that we have here, we have dV dt, we have the radius. The thing that we are missing here is actually two things. We don't have the height or the dr dt. So there's a problem. Over here, we can fill in our pi and our r, and we know that we're looking for our dH dt. So our problem lies here, which kind of would have been the same problem that would have happened up here if we had used the product rule. But if we think about what's happening in this problem, it actually doesn't end up being quite a problem that we don't have two variables over here or two unknowns, because if we think about this cylinder as kind of being like a tank, so think about it as being like a metal tank holding water. As the water level is rising or dropping, the shape of the cylinder is not changing. So this water tank is not being expanded or condensed at all. So what we know is that no matter what happens with the water level in this tank, this radius is not changing, which means that our dr dt would actually be a 0, because this rate of change of the radius is going to be 0. It is not changing at all. So basically what happens is when we use the product rule, even though we don't have h or we didn't have dr dt, if we know that dr dt is 0, it really doesn't matter what the rest of the stuff is over here, because what's going to end up happening is this term is going to be going to 0. So let's see. So our dv dt is 3. We know we have our 2 and our pi, and we know that we have our radius of 5. We don't have our height, but we know that the dr dt would be 0, which means that this whole term would end up going away anyway. Over here, we have pi times our radius of 5 squared, and we know that we're looking for dH dt. So what we end up simplifying is just 3 is going to be equal to 25 pi dH dt, and then we can multiply by this, or we can divide by 25 pi on each side. So our dH dt would end up being 3 over 25 pi. And then since this is just a height that's changing, again, that's just a length or a distance, our units would be meters per minute. So we actually have another method similar to what we kind of took an approach to up here with this cone problem. What we can do is we can actually account for the constant r in our first step. So we know that our volume is pi r squared h. If we know that this radius is not changing at all throughout this problem, what we can actually do in this first step here, kind of what we did up here is we kind of substituted in to get rid of one of the variables. If we know that this radius isn't changing, we can actually just right off the bat say that this is going to be pi times 5 squared times h. So we can actually rewrite our volume formula as 25 pi times h right off the bat because the radius is not changing. That's going to be a constant throughout the entire problem. So then our differentiation of this actually ends up being a lot easier. If we take the derivative of v, that'd be dv dt. This 25 pi again is just a constant. And then I'm multiplying by the derivative of h, so dh dt. And then here, this ends up being pretty similar to what we get down here, which took us kind of like 3 steps to get there. Our dv dt is 3. That's going to be equal to 25 pi times dh dt. Again, just dividing by 25 pi on each side tells us that our dh dt here would still be 3 over 25 pi. And again, our units would still be meters per minute. So regardless of which way you do it, you should still come out with the right answer. It's just kind of up to you of which way you want to go. Product rule will probably take you a couple more steps and take you a little bit longer. And then you would have to kind of think about what's going on here in terms of rates. And then one of your pieces would end up going away, regardless of maybe not even knowing what one of the variables is. All right, so it is your turn to try some practice for homework. Let me know if you guys have any questions.